you initiate a response to hypoxia. Oxygen. So you own dependent degradation domain. Say that this is the oxygen dependent degradation domain. domains. So let's say that this is the oxygen-dependent degradation domain. So basically, this degradation of this hypoxia-inducible factor 1 alpha is dependent upon the presence of oxygen. So you only destroy the hypoxia-inducible factor 1 alpha if there is oxygen present, and when there's no oxygen present, i.e. in hypoxia, you won't destroy the hypoxia-inducible factor. One alpha, okay, and that's how you initiate a response to hypoxia. Okay, and it should be oxygen dependent with the dash there rather than between the dependent and the degradation. So oxygen dependent degradation, and I'm spelling this wrong, degradation, why has that got an I in there? Degradation, and then it's the domain, so the oxygen-dependent degradation domain. And for short, the oxygen-dependent degradation domain is known as the ODD domain. Okay, so O for oxygen, D for dependent, and then D for degradation, so the ODD domain. So this special domain here has two proteins in which are going to be hydroxylated under conditions of normoxia. So when oxygen is present,
Surrounds erythropoiesis. It's increased RBC.
you will destroy the hypoxia-inducible factor 1 alpha. When it's not present, you won't destroy it, and that's how we're going to respond and detect
Abundant O2 bind to the oxygen degradation domain, destroy HIF1 alpha, hence HIF1 dimeric protein does not exist, cannot stimulate erythropoietin, increase IBC, hypoxic levels, low levels of O2, cannot destroy HIF1 alpha, hence HIF1 dimeric protein will exist. HIF1 dimeric proteins exist HIF1 stimulates the point to increase RBC.
The hypoxia. Okay, so basically, in this oxygen-dependent degradation domain, there are two proline residues which are going to be hydroxylated.
Therapeutic targets.
And this is going to lead to the destruction of this hypoxia-inducible factor 1 alpha. So destruction of this hypoxia, and this
HIF1 alpha oxygen dependent degradation zone. The HIF1 alpha oxygen dependent degradation zone.
oxygen. Okay, so basically, in this oxygen-dependent degradation domain, there are
Domain.
two proline residues which are going to be hydroxylated, and this is going to lead to
Proline
residues which are going to be hydroxylated. And this is going to lead to the destruction of this hypoxia-inducible factor. The 1 alpha. So basically you have a proline residue at position 402. And you also have a proline residue at position 564. Okay, so what that means is if you imagine that this hypoxia-inducible factor 1 alpha, even though we've imagined it folded up, it is fundamentally a polypeptide. It's a polymer of amino acids. So you can count the amino acids, so you can start with the first one, the second one, you can count all the way up to the 402th one, and then you can go onwards to the 564th one. If you look at the 402th one and the 564th one, they will both be proteins, basically. So you'll find a protein here and another protein here. And these proteins are going to be hydroxylated. Okay, and I'm going to explain the process of hydroxylating proteins. Okay, now you might have heard of something similar. To this before, and in fact you will have heard of something, well, you might have heard of something very similar to this before, which is that collagen, a very important protein in connective tissue, collagen has hydroxylated proteins, and basically the modification is the same as is in collagen. Basically, we're going to put on a 4-hydroxyl group. Okay, so let me show you the structure of a normal proline residue, and then I'll show you how we're going to hydroxylate it, and then we'll discuss the enzymes which are going to hydroxylate it, and we'll discuss how this process is going to be oxygen dependent. Okay, so we'll start off with the structure of a proline residue. So here's the amino group, here's the alpha carbon, here's the carboxylic acid group, and we're drawing a proline residue, so we're imagining that this is within a protein, basically. Okay, so the amino group and the carboxylic acid group will be bound to amino groups and carboxylic acid groups of other amino acids by peptide links. And off the alpha carbon you have a hydrogen, and then the R group in proline is basically this ring structure, like so. Okay, a 5-membered ring structure. And off these carbons you then have hydrogens coming off. Okay, like so. Right. So this is the structure of proline. This is a normal proline residue. And basically what we're going to do is we're going to take one of these hydrogens off this carbon and put on an alcohol group instead. So we're going to convert it to what is called 4-hydroxyproline. And I'll discuss the reaction that you actually use to do this in a moment. Okay, so 4-hydroxyproline will have an alcohol group coming off this 4th carbon, because this carbon with the carboxylic acid group on, that's considered the 1st carbon, then the alpha carbon is the 2nd carbon, 3rd, 4th. Okay, so we're going to add an alcohol group onto this middle member of the ring, basically. So let's draw out the structure again. So here's the amino group, here's the alpha carbon. Let me just move this up a little bit. Okay. Here's the carboxylic acid group, which will be linked with the amino group of the next amino acid along. And then we've got this 5-membered ring here, like so. And then we've got an alcohol group now coming off this 4th carbon here, and 1 hydrogen also. And then 2 hydrogens off this carbon, and then also 2 hydrogens still off this carbon. So this is the structure of 4-hydroxyproline, and this is what's going to happen to the proline at position 402 and the proline at position 564 in the oxygen-dependent degradation domain of the hypoxia-inducible factor 1-alpha. Again, this is normally happening in a normoxic cell where there are normal oxygen levels. This is happening, and this hydroxylation of the proline residues is going to lead to the degradation of the hypoxia-inducible factor 1-alpha. So, how does this reaction work? Well, basically, you also need, as a co-reagent, you also need 2-oxoglutaric acid, which is also called alpha-ketoglutaric acid, and it's a member of the Krebs cycle, basically. So 2-oxoglutaric acid. So glutaric acid, okay, is the name for a carboxylic acid where you have 5 carbons and carboxylic acid groups at each end of the molecule, basically. So let me show you the structure of this. Okay, so here is a carboxylic acid group, and then we need 5 carbons in total. So here's the 2nd one, the 3rd one, the 4th one, the 5th one. And then we need a carboxylic acid group of carboxylic acid H base this carbon. Okay, so imagine acid group to this carbon here. That will create bonds back to this oxygen and 2 back to this other oxygen. Then bind one of these oxygens to this carbon, which also has 2 free electrons to create carbon dioxide. Then bind this oxygen. Well, actually, firstly you're going to have to cut off one of these hydrogens. Cut the wrong one, damn it, but never mind. Cut one of these electrons of the oxygen. Okay, and that's how this reaction makes sense. Oxygen atom, which has 2 free electrons, and bind it both to the carbon, and then the hydrogen can bind to the other oxygen, the other free electron of the oxygen. Okay, and that's how this reaction makes sense, basically. The things on that side add up to the things on this side. Okay, right. So this is the hydroxylation of proline residues. In the next video, what we'll do is discuss the enzymes which catalyze this reaction, and we'll also discuss what happens under hypoxic conditions. Okay, so welcome to this next video in which we are discussing hypoxia-inducible factor. Okay, so we've discussed that hypoxia-inducible factor 1 is made up of two proteins, hypoxia-inducible factor 1 alpha and hypoxia-inducible factor 1 beta. And if you produce hypoxia-inducible factor 1, then you will initiate the response intracellularly to hypoxic conditions. Okay, now the reason you don't usually initiate the response is because you don't usually have hypoxia-inducible factor 1 complexes in the cell. And the reason is that hypoxia-inducible factor 1 alpha is usually degraded the moment it's synthesized, basically. So hypoxia-inducible factor 1 beta is always present within the cytoplasm of cells, but hypoxia-inducible factor 1 alpha is not. And the reason isn't that it's not synthesized. It is synthesized, but the moment it is synthesized, it is destroyed. Okay, and we're currently in the process of discussing how it is destroyed. So basically, we discussed that hypoxia-inducible factor 1 alpha has this special domain known as the oxygen-dependent degradation domain, the ODD. Okay, and within this oxygen-dependent degradation domain, you have proline 402 and proline 564, and these prolines will get hydroxylated on their fourth carbon, like so. Okay, and this process requires oxygen. Okay, so this process will only occur in the presence of oxygen, and in the presence of hypoxic conditions, when there's a low oxygen, then the reaction will not occur, so the prolines will not get hydroxylated, and the hydroxylation of the prolines is essential for the degradation of the hypoxia-inducible factor 1 alpha. So, we just want to discuss the enzymes which catalyze this reaction. So there are 3. However, the enzymes which catalyze this reaction are far more complicated than that, but it's not that they actually are more complicated than that, it's that their naming systems are quite complicated. So basically, for each one of these 3 enzymes which can catalyze this hydroxylation of the prolines, there are 3 different names. So the first naming system is the prolyl hydroxylase domain enzyme naming system. Okay, so in this naming system, the enzymes which catalyze the hydroxylation of the proline residues are known as prolyl hydroxylase domain enzymes. Okay, and for short, prolyl hydroxylase domain enzymes are abbreviated to PHDs. Okay, and this is the most popular naming system for these enzymes. So there is PHD1, so prolyl hydroxylase domain enzyme 1. There is prolyl hydroxylase domain enzyme 2. And then finally, there is prolyl hydroxylase domain enzyme 3. Okay, but there are other naming systems as well. So another naming system for these enzymes is the hypoxia-inducible factor, the HIF, prolyl hydroxylase. Okay, so you'll also see these enzymes known as hypoxia-inducible factor prolyl hydroxylase enzymes. And for short, the hypoxia-inducible factor prolyl hydroxylase enzymes are abbreviated to the HPH enzymes. Now, what would be extremely simple is if PhD1 was called HPH1, and if PhD2 was called HPH2, and if PhD3 was called HPH3, but it is not that simple, unfortunately. PhD1 is called HPH3, okay? PhD2, thankfully, is called HPH2. PhD3 then is called HPH1. So the numbers swap around, basically, unfortunately. And it doesn't stop there. There is another name for these enzymes, and this is the most ridiculous one. Okay, the other name is to call them the egg-laying 9 enzymes. Okay, and for short, egg-laying 9 is abbreviated to EG for egg, L for laying, and then N for 9, so the egg-laying 9 enzymes. Okay, and what numbering system do we have here? Well, PhD1 or HPH3 is also known as, egg-laying 9.
What?
And unfortunately, it's the one remaining one. It's egg-laying 9 too. So it's got different numbers in all the different naming systems, unfortunately. PhD2 or HPH2 is also called egg-laying 9 1. So